This video is for section 7-2, rational and irrational roots. Recall that a rational number is a real number, such as 3/4, 2 1/3, or -9, which can be expressed as a ratio of integers. Can you express numbers such as the square root of 2, the cube root of 5, and negative the fourth root of 3 as a ratio of integers? If not, then they are not rational numbers, they are called irrational numbers. These three roots, the square root of 2, the cube root of 5, and this one, are roots of the following equations. Let's find out if they are rational. Before we do, let's discuss a theorem about rational number roots. And we'll use this example to lead into the theorem. The rational number 2/3 is a root of this equation, because when you substitute 2/3 for x, it solves the equation, as you see on the screen. Do you notice two things about that root 2/3? The numerator, the 2, is a factor of the constant term. -20 does divide evenly by 2. The denominator of our root, the 3, is a factor of the leading coefficient. The 21 divides by 3 evenly. It seems like that for a rational number to be a root of an equation, the numerator of the rational number must be a factor of the constant term, and the denominator of the rational number must be a factor of the leading coefficient. That's what this theorem says. Most textbooks call this the rational roots test. If p and q are integers, so that p over q represents a rational root of a polynomial equation, then the p must be a factor of the constant term, and the q must be a factor of the leading coefficient. So let's go back to our original question. Is the square root of 2 a rational number or an irrational number? The square root of 2 is a root of this equation, because you would solve this equation by taking the square root of both sides. The square root of x squared makes x, and on the right side, the square root of 2 makes the square root of 2. To know if this solution is rational or irrational, let's use the rational roots test. The rational roots test talks about polynomial equations in standard form. So let's take this equation and change it to standard form by subtracting the 2 so that there is a 0 on the right side. Any rational number roots of this equation will be ratios of integers, where the numerator is a factor of the constant term. Factors of -2 include positive or -1 and positive or -2. The denominator of the rational root must be a factor of the leading coefficient. And there's no number here, so that's automatically a 1. Factors of 1 are positive or -1. When you consider the different combinations represented here, what numbers is this actually identifying? A +1 over a +1 is the number 1. A -1 over a 1 is the number -1. A +2 over a +1 is the number 2, and a -2 over a +1 is the number -2. If the numerator can be any one of those four choices, and the denominator can be either of these two choices, then the possible rational roots are 1, -1, 2, and -2. Notice that the square root of 2 is not one of those four possibilities. Therefore, the square root of 2 is not rational, it's irrational. The answer to this question is no. Another number from earlier that we wondered if it was rational or irrational was the cube root of 5. And we said that the cube root of 5 would be a solution to this equation, because to solve this equation, you could take the cube root of both sides. The cube root of x cubed is x. So x equals the cube root of 5. But is this rational or irrational? Let's take this equation and rewrite it in standard form by getting a 0 on the right side. Any rational roots must be fractions where the numerator is a factor of the constant number -5. Factors of -5 include positive or -1 and positive or -5. The denominator is a factor of the leading coefficient, and the factors of 1 are positive or -1. Let's consider the different combinations of numerator and denominator. 1 over 1 makes 1. 1 over -1 makes -1. 5 over 1 is 5. -5 over 1 is -5. These are not the solutions to the equation, but these are the possible rational roots. If it has rational roots, it must be one of these 4 numbers. The solution that we figured out earlier is not one of those 4 numbers, therefore this number cannot be rational. The answer to the question is no. In general, this expression is irrational unless the radicand is the nth power of an integer. For example, if n is 3, we have a cube root. If b is the number 8, then this is rational because the b is 2 to the 3rd power. The power is matching the index. On the other hand, the cube root of 9 is irrational. What about the square root of 25? Is that rational or irrational? That's rational because that is equivalent to the square root of 5 to the 2nd power, and the index matches the exponent. This turns out to just equal 5, which is a rational number. Let's summarize the lesson. We discussed irrational numbers, which simply means numbers that are not rational. And we discussed the rational root test, which is a technique to find a list of possible rational solutions to an equation.